start today for once. I think that's as big as it gets. Okay. Anybody have any questions or comments? We've been working on a kind of a package of tools to use higher order programming. So we looked at map and filter. There's really just one thing missing from that. You often hear these things put together, map, filter, and reduce, or maybe just map and reduce. And for a long time, Google called their architecture map reduce. They don't use that anymore, but still it's a major paradigm in programming. It's a way of organizing things at a large scale and a small scale. Reduce is, you just use the special case of fold. So fold is the thing we're going to be looking at. You probably didn't see this in Python, simply because fold, it's doable in Python, but the stuff that surrounds it in the language doesn't really make it that useful or an appropriate way to do things. And plus, there are some major efficiency concerns with using it. Haskell is very good at optimizing uses of this fold operation. Python is not, and that's just a design choice. They focus on things like loops to write things efficiently. All right, so today's mostly looking at fold. We're going to look a little bit at this concept of tail recursion too, which is a way of trying to emulate loops inside of Haskell. And it works in any functional language. As we'll see, it's actually not very useful in Haskell. It looks like it should be, because essentially it is getting rid of recursion in the sense of building a big call stack of stuff. And doing something that looks very much like the iteration you have in loops. But because of Haskell's lazy computation, it's in many cases actually worse than writing something that uses normal recursion. So we'll see some examples of that. The reason we're doing tail recursion is simply because it's a standard, efficient way of doing things in most functional languages. So Haskell is really the only functional language out there that uses lazy computation. There's a lot of other languages you might have heard of, like ML or Scala or what else? F#. Those are all call by value languages. And they have some imperative features thrown in too. By call by value, I mean you evaluate the arguments of a function call before you call the function. So having a lazy computation like in Haskell, where you postpone evaluation as long as possible, that really changes the efficiency considerations, and in particular makes this tail recursion topic not so interesting. So we've looked at a bunch of examples of data types. We looked at map just in terms of lists, but you can actually generalize it to a lot of other data types. And, you know, what's map doing? You have these lists that have some element type, that have elements with some type, given type A, lists over A. And you don't care what those things are when you're just writing list operations. So when you're doing map, for example, it doesn't matter what those elements are. We get to say you're writing the map function using recursion. All you're doing is running through the list and applying the function. You don't care if the values are integers or whatever. You're just applying the function, taking whatever it gives, and sticking that in the list spot. All right. So you're treating the element type for list as a kind of an abstract thing. We're doing some operations that work for lists, independent of what the actual element type is. And Haskell forces you to do that too, right? If you have a type parameter in a data structure, I've given you kind of an example of data structure here. If you look at this type argument here, this is like just a type parameter. It says, ds of a this is a type for any type A you might want to stick in there. But you can't do anything based on what that type actually is. There's no way to, you can't ask, if it's the integer type or a list type. You can't say, if the type A is integer, then do one thing, otherwise do something else. Right? There's just no operations Haskell gives you for that. So what you can do, so what that means is that this, this A is kind of an abstract type here. Can't ask what it is. Say programs or the type. Maybe we'll say programs that, functions that take, say, something in ES of A and give you some other type. Lists aren't the only thing with this kind of embedded type. So lists have this embedded element type, but there's other types we've seen that also have these embedded values from another type where we don't care about what that actual type is, right? We saw binary trees that had leaves with some information, some keys in them, trees that had keys in the internal nodes and in the leaves. And you can imagine all sorts of other data types. A very simple one is maybe. So that's a little odd one because, a little different than the other ones because trees, for example, every tree will have some these values embedded in it, but maybe, a value of the maybe type, maybe does, maybe it doesn't. So if it's just nothing, then there's nothing in there, but if it's just of something, then it has one value there, right? But the point is that values of the type can have, one or multiple occurrences of this external type that you're plugging in as a parameter. And whenever you have that, it makes sense to have a map operation. You just go in, find the occurrences of things from that type, and then apply a function to it. Just like you do in lists. So some examples I just gave were tree leaves, tree info, key items, and fields of a database too. You can actually do, you've probably seen databases before, just tables. Tables of rows where each element of the row can maybe have a different type. But you could imagine going in and say, apply this function to the first column in all of these tables, all of the elements in the first column. So that's again, it's the same, conceptually the same thing. Takes the function, applying it to parts of a data type. So if you think of a little more abstract view of this data type, ds of A is just supposed to give you a kind of typical example of this. You'll have some constructors, they take arguments of certain types, and inside those types you'll have occurrences of A. And where you have those occurrences, that corresponds to spots in the data structures that you build up, and you can think of mapping a function over those. So, one of the things that we're trying to do in this part of the course is to give a couple basic operations for doing a big range of functional programs. So we talked about map. As we just said, it's a kind of, you can think of it as a programming pattern, if you like, but it just captures that pattern in one single function. Mapping something over parts of a data type. I put this down as a limitation, but it's what map does, so I don't know if it's fair to say it's a limitation, but what it doesn't do is, it doesn't know anything about the context. Right? When you're mapping something on a list, it goes through each element and then applies the function to that element. But you don't know where that element is in the list, you don't know what the surrounding members are. It just does each part in isolation. So what we're going to look at is something which addresses that sort of limitation, is the fold abstraction. And the way you can think of it is just really a beefed up sum. So the sum example is really easy to understand. You have this in Python as well. It's summing up the elements of a list. List of integers, add them all up. And defining it recursively, quite straightforward. Sum of an empty list, say that's 0. If you want to sum a list of something followed by a bunch of other things, then it's that first thing plus the sum of the other things. It's just a very, very straightforward recursion here. But if you think of this in the abstract, these two parts here, those are just, you can just think of these as examples of what you might put in. You can put all sorts of other stuff in there, right? Like if I took this same pattern here and replaced plus by times and maybe 0 by 1, it would still make sense. Now I'd be multiplying all the elements together, taking 1 in the case, or having the result be 1 if it's the empty list. Right? So we can generalize these things here. And just one example is we could take 0 and replace it by 1, and we take plus and replace it by times. But any operations of the correct types would do. It doesn't even have to be integer, right? It could be anything. And it doesn't have to be something which is giving just a simple data value like a number. It could be something that's actually building another data structure. So that's exactly what we're going to look at, is what's the right way of generalizing this, and what are some of the things that you can do with it. And if you want to think of this in the abstract, it's instead of mapping something on each individual element from this external type, you're thinking of those elements as being kind of laid out in some order. So you can imagine like a binary tree where you have keys to the leaves. You can think of the leaves as being in order from left to right. You have some way of traversing those parts that have those elements of A in them. And then you can take an operation and try to accumulate a result. Start, with the first two, and then you add those, it adds your operation, and you add the result of that to the next one, result of that to the next one. And so you just traverse through a list of these things of this type A, applying this binary operation as you go to accumulate a value. Now that's really all that's going on. We're actually just going to focus on lists right now. But the application to other types is quite straightforward. In fact, one way you could just think of doing, say, a fold operation for trees, where you wanted to accumulate some value over the leaves of the tree, the keys of the leaves, would just be to write a function which gets all those leaf values, puts them in a list, and then does the list fold operation. That would be equivalent. All right. Yeah, I just wanted to just briefly say a little more about how mapping works for other data types. I wave my hands about it, but this makes it just a little more precise. You could imagine having a map operation like this one for any type that has parameters. So maybe you can define it easily, maybe you can't, but at least makes sense to think of this map type. You'd have to give a separate definition for every type that you give. T is just some type here, but just some type constructor we defined, some data type, so some type defined using the data type constructor. And it has some type parameters. We've seen things with 2 type parameters, I think. We've had maps, for example, map of AB. You can have as many type parameters as you want. And I've picked out the first one here as a special one, but you can do the same discussion with any one of these A1 up to AN. So I wrote here things AI instead of A1. But just focusing on the first one, it makes sense. A member of this type T, A1 up to AN, it's going to be some kind of data structure, who knows what it is, but inside it'll have some members of A1 probably. Otherwise, why would you put that parameter in there? So it has these members of A1, and it makes sense to go in and take each one of those and turn it into something else by applying a function to it. If A is integers, maybe you add one to it, but we don't know its integers at this general level, but you could have an instance of it where A1 is replaced by the integer type, and then you might want to replace those integers by the integer plus 1. Okay, so it makes sense to do a map here, and it really works, the same way as mapping over lists. You take a function, some function which turns elements of A1 into elements of B somehow, and then you just go in the data type and you make that change, and then that gives you a result where that A type, this type, since you've gone in and applied to every thing in the data structure that has type A1 and applied a function that returns B's, then you end up with the same data type, but the elements of that were A1 are now B's. Okay. And here are just some examples of how this works out for a variety of types. Some of these I referred to just a minute ago. The tree AB. A is the type used for a key that you stick in leaves. B is a key that you stick in a node. You have leaf, you have a node which is so 2 subtrees as we looked at before. It has an arbitrary number of subtrees. We're representing that as a list. Okay. So tree's either a leaf or it's an interior node with a key in it and then some list of subtrees of children. So you can write 2 different map functions, one which goes in and changes all of the leaf keys to something, and one which goes in and changes all of the keys in interior nodes to something, right? And that has the obvious types. You have a function that turns A's into C's, and you take a tree with A's and B's in it, then the A's have been turned into C's. Map maybe, the same deal. The maybe is either nothing, in which case map maybe just returns that nothing. Or it's a just of some A, just applies that function to that A element and gives you a B element. So now you have just of something in B, so it's a type maybe B. This either type, I don't know if you looked at it before, but it's either just left of A or right of B. It's 2 different, it's just a way of tagging, kind of doing a union where you've tagged the elements. So if you look at something in either type, you'll see it's either built with left or right. If it's built with left, you know it has an A element in it. If it's built with right, you know it has a B element in it. Anybody like to see a definition of any of these just to make it concrete? Or? Let's see. Okay, one head nodding and no heads shaking. So let me just do, maybe I'll do this tree one here. Map tree one, so just do a standard definition by recursion. So map tree, let's make it extra interesting. Do map tree 2. So that's taking a function from B's to C's. And it takes a tree as its main argument. And just use our standard pattern matching recursion. That's either leaf of something. Okay. Write down the 2 parts of the standard pattern here. It's either leaf or it's node or something. Actually, I'll put in the actual value here. So leaf with some key K, or it's a node. Which has some key K and then a bunch of subtrees. So we'll call those trees, I don't know, TS. All right, so we've got this function which applies to B's, things in B. Leaf K, K is an element of A, so we can't apply F to it, so we just leave that alone. What we want to do is we want to apply this function to the information field or the key that comes with interior nodes. So that stays the same. And in here, We're building the same node again, but now we're using the key where we apply F to the key that was already there. And then the last argument here has to be the recursive result of doing the same replacement in the subtrees. And so for that, well, it's just a list. We want to change each of the subtrees into the result of mapping over those subtrees. So that's just the regular list map function. Right? So just map. Come on. Right, so you want to map something over the subtrees. And what is that? It's something which map trees this F over each of those subtrees. Remember, we can think of this as being an entity by itself. What's that? Map tree to F is just a function which takes a tree and then does the mapping, returns the tree that's the result of doing the mapping. Or you could write lambda in here as well, like lambda with an explicit tree argument. So it's a little more compact to write it this way. So here we just have map tree to F. So you want to map that over the subtrees. And that's all there is to it. Okay, so you're taking this thing which recursively applies the function to the B fields of a tree, and you're mapping that on all the subtrees. So if you understand that, then really introducing new data types with these parts in them, it goes exactly the same way. You're just doing the standard recursion pattern, pulling the things apart, and then applying F to the right parts and rebuilding the whole thing. That's all we're doing here, right? Here we're just taking, here we know in the leaf case, we're just rebuilding the same thing, returning the same thing. In the node case, we just go in and apply F to the key part, and then rebuild the node, and also apply, recursively do our work on the subtrees. Okay. This is a bit of an aside here. I don't expect anybody to really understand this at this point. But an interesting question that comes up is, what kinds of types could you actually write one of these map functions for? You're probably used to this in Java, right, where you write interfaces. If you have some operations in mind that turn out to work on a variety of different classes. A good classic example is stringify. I figure maybe that's not the name in Java, but most classes that you define will have some stringify method, a method which will take an instance of that class and give you something suitable for printing out, like a nice string, documentation string or something, right? So it makes, you may want to write programs that work with any class for which that has a stringify method. And that's what Java interfaces are for. You say, well, let's call this the string interface, stringify interface, and something satisfies that interface, some class satisfies it if it has a stringify method. What that means is that now you can write these functions or other abstract operations that assume there's a stringify method and do something else with it, some higher level, print out or something like that. So it's exactly the same thing in Haskell. We'll see a little more about how that's actually done. They're called type classes in Haskell. They're not like Java classes, they're like Java interfaces. So when you have something like this, you're thinking of, there's a bunch of types that I know, where I know how to write a map operation. It might be useful to have those types kind of collected so I can write operations which work with types that have a map operation. So maybe if I know there's a map operation, I can do other stuff, other useful things. So what types have a map operation? Well, it's really exactly the same as you would do in Java. A map operation, something which is in this class, is just something that supports a map operation. So this is supposed to be a type constructor here. We'll say a lot more about type classes later. This is just kind of a preview, if you like. So we're thinking of this T here. This is not a type in this setting. This is actually type constructor. Print that out here. Type constructor. A type constructor is something which, you know, takes a type and gives you another type, builds a type from a given one. So for example, you know, the list type constructor is one you're familiar with. Or maybe is a type constructor. Because you can think of this as being, you know, that's the operation that takes some type A and gives you lists over A, or the maybe operation, you know, takes some A and gives you the type maybe of A. All right, so it's just a way of building types. So if T is some arbitrary way of building types, we're going to say it's in this functor class, exactly if it supports a map operation. And the map operation has the kind of type you'd expect. We're talking about this type constructor, which, you know, here it's we'll have types built with A components, wherever those are, you know, it could be list elements. Here, this is the same type, but now with B components. And you get from one to the other by mapping this function over the A components. You know, somehow, you've defined a function, fmap, for some particular type constructor T, which goes in and replaces A's by f of A's for any f you might take. Right? So that's called fmap, and the reason it's not called map is simply because, for historical reasons, map is hogged by the list map. So the list map that's built in Haskell actually is, if you write fmap for map, it'll work the same way. So map is the, I'll just make a note of it here. So map is just this fmap function, particularized for lists. And so I can, you know, I can write fmap +1 over 1, 2, and that gives me the list 2, 3. Okay? But fmap works on any type for which it's been defined. And that's up to you, right? When you write a bunch of programs and you introduce a bunch of new types, if you have a way of mapping over those types, you would just define an instance of fmap for that. You would say, for this particular type, fmap equals this. And then the compiler takes care of actually applying that. The compiler, when it looks at fmap applied to something, it says, okay, what type does that have? Is there an fmap already defined for that type? If so, I'll use that. Otherwise, it's a compiler error. I think it's let's see how easy it is to switch here. It's supposed to just be able to do this. That up. For one of them. It's the, which one's switch? Well, it's not very quick, is it? Okay. So you can, I think we looked at this yesterday, this info thing in GHCI is quite handy. We looked at this functor type class. You can actually ask for information on it. Info functor. Right. So here's the definition. I actually had put it on the slide as well. But here's the definition. This thing here, actually gives two operations. What this is essentially saying is that, you know, and also uses f here instead of I use t. That's something we've been using for kind of object level stuff. We didn't usually use that as a name for types. But just think of this as being a t if you like. It's a type constructor. It's saying that the type constructor is one of these functors if it has a map operation and this thing here. But you notice there's this little comment, it says minimal. So to define an instance of this, you just need to provide the map operation. That's the minimal thing. And if you don't provide this thing here, then it'll define it for you because it's just derived from the first one. I'm not sure how useful this thing is, but it's a binary operation that takes an element of A and gives you something, and something in this, think of that as being lists here. So it takes an element of A and gives you something in a B list. Or sorry, takes an element of A, takes a B list, and then gives you an A list. So you can imagine there's really only one kind of function that, well, I guess there's some choices, but there's not many functions that would fit that type. It's one of the interesting things about Haskell is that, since you can't discriminate on what the type is, right? So if I'm writing a function of type A or O, F, and B, I can't do special cases on what A is. It has to work for any possible A. If I can't even ask it, I just have to treat it as like this little atomic black box thing I'm getting, this element of A, and then I can pass it around and build other stuff with it, but I can't actually look inside it. Right? So that gives you, the types actually tell you a lot about what the thing has to be. So I don't know what A's are, and I've got this list of B's. How do I get a list of A's out of that? So I give you an A list of B's, you need to come up with a list of A's. Well, one stupid way would just be to return the empty list, right? The empty list is a list of anything. What about something that's non-empty? So you need to come up with a list of B's. So the elements have to be B, sorry, a list of A's. The elements have to be, of the list have to be of type A. Where you're going to get something of type A. You can't make one up, like you don't know what A is. If it's integer and they say, okay, 0, that's, but if it's just some arbitrary thing A, you have no idea if it even has an element. There's no way of coming up with an arbitrary one. Right? So the only way you can put something in a list is to use the thing that you're given. So you're given an element of A, and that's all you got. It's the only way of coming up with an element of A. So you need to make a list, and they all have to be A elements. All you've got is that input. So you just use that for all the elements. So what this in fact does is just takes a list where the elements have some type and just replaces all those by the argument of type A. Right? So if I had, if I was applying this function to 3 and I gave it a list of strings, the output would be a list of 3s, the same length as the list of strings. Not clear to me why that's useful, but they seem to have gone to some lengths. They reserve notations like these for things that they think are useful, so there must be some use for it. All right, the reason I brought this up, the main reason I brought it up was just to see that there are some instances already defined in the standard prelude. So these functions, these different types that were defined, like maybe and either, and the list type constructor here, those have an instance of that map defined for them. Something, I'll mention this on the next slide here. These are not so surprising. Actually, let's just look at this one here. So this first part here is just a way of writing pairing as a type constructor. So paren, comma, paren. That's something that takes two types and makes a pair type. Right? So paren, comma, paren applied to int. String will give you the type of pairs of integers and strings. And that has a map operation defined. But the one thing that's odd here is that the map, if you look at the type of map here, it says, well, we're talking about type constructors that only take one argument. So in pairing, that's something that takes two arguments, right? So pair A, B is pairs of A's and B's. So how is that a one argument type constructor? Well, this concept of currying applies at the type level too. So you could think of pairing of a type A as a one argument type constructor. Think of it as the int. So if I take pairing and apply it to int, that is a type constructor which takes any other type and pairs it with int. So if I take pairing int and apply it to string, I get int string. If I take pairing int and apply it to bool, I get pairs of int bool. The odd part of this then is that you really, yeah, this is a functor then, this application of the pairing type constructor to some given type A. This is something which will take B's and give you pairs of A's and B's. But the map operation, what does the map operation do? The map operation applies this given function to the argument of the type constructor. So if the type constructor is pair of int, what that means is that the map thing you're going to write is going to work on the second element of the pair. So you have a function, f, which maps B to C, and you have this type constructor, pair of A applied to some B, so that'd be pairs of A's and B, A's and the B thing. The map thing just applies to the B thing. So that's a little abstract, but the point here is that there's some arbitrariness here. Like the definition of mapping here doesn't allow you the full generality of what you might think. You might want to map on the first element. But if you want to use the built-in fmap, it only works on the second element of the pair. Right, so it's worth thinking about it. If I think it's a little too hand-wavy to really understand completely at this point, but it is worth thinking about, just to get the notion that this concept of currying also works at the type level. You can think of two argument type constructors as one argument type constructors applied to another argument. But it also means, it points out a limitation of the way things are done in Haskell, and that the order of the arguments matters. And here's an odd one too. This is something actually I have a slide about this. Let me not say anything more. The solo type, I have no idea what it is. Anybody know what it is? Maybe info will tell us. It's a mysterious sounding type. Oh, what? Not in scope solo. I get GHC. These. Nah, come on. All right, I think we'll remain a mystery. Okay, let's see how long it takes to get back to the computer here. I thought I had oh yeah, so it's just a note on this slide. So I'm not going to go through this. I think if you're interested in this kind of thing, it's kind of I don't know if abusing is the right word, but it really is an odd way of thinking of mapping. So this arrow C, what this is the type constructor, which takes any type A and gives you A arrow C. So you think of C as being some fixed type for this. So it takes int and gives you int arrow C. What is the sense of a map operation for that? And that doesn't really fit what we talked about before, because it's not so clear now. If I take this type constructor and apply it to int, say, okay, I've got int arrow something, but where are the elements of int buried in there? It's not like just a normal data structure. Now you've got this function. Right, but still, the concept makes sense. The type makes sense at a higher level, I guess, and the type makes sense. So you can ponder what it actually all means and why it's useful to think of that as a mapping operation. All right, so let's get on to fold now. So to get really concrete here at the beginning, there's two views of the sum operation. Let me go back to the definition that we had at the beginning. So we're just thinking of the standard recursive definition sum. Sum of the interlist is 0, otherwise first thing plus sum of the remainder. And if you think about how that computes, just using our usual kind of equational reasoning approach, Each one of these lines here just follows by applying the definition of sum, pattern matching, right? It says, well, first list non-empty, so it's the first thing, 1, plus the result of recursively computing the sum of the remainder. Okay, so 1 plus sum 2, 3, and then you just keep expanding sum out. And you get this big line here, 1 plus 2 plus 3 plus 0. Some of the stuff, when we're using these a more general list, say with a bunch of unknown number of elements, we're going to use a lot of dots. And for full generality, we need to put parentheses in, but that could get pretty ugly. When an operation is associative, I should make sure that everybody knows what associative means. Associative. Let's call it associate operator. Maybe let's call it op. It's just defined to be something where if you just have a string of things put together with that operator, it doesn't matter how you parenthesize them. So the basic law for that is just it has to look like this. If I take, say an add, so not an adding, if I'm combining 3 things using op, it doesn't matter where I put the parens. So x1 op x2, if I take that and then take that result and then combine that with x3, it's the same thing as writing x1 and then doing that the other 2. Okay. And so that's certainly true for plus. So what are some associative operators that we know? Well, plus is 1 times. Minus is not. Minus depends on where the parentheses are. X minus A minus B. If you put parentheses around the second 2, X minus Y minus Z, putting parentheses around the Y minus Z is different. You get a different result. You can work that out if you like. Any other associative operations that you know? It's one that we've been using for to do with lists.
Multiplication? Multiplication?
Yeah, multiplication I got here. That's a good one.
Modulus?
Modulus. No, I think probably not. One for lists. Looking for one for lists. What's the most common operation for lists? Takes 2 lists and gives another list.
Cons?
It doesn't take 2 lists. Operation combines 2 lists. Append. Take 2 lists and put them together. Right? So that's associative, right? If I think of appending a bunch of lists, all I'm doing is stringing them out one after the other. So it doesn't matter what order I do it in. If I string out the first list and then the second one, and then add the third one, or if I do the second and third and then put the first one in the front, it's all the same thing. So this plus operation for lists is another one. In describing fold, it's going to be convenient to use this miraculous dot notation. You certainly see it in math courses. It's not the most precise thing in the world. You can, if you're disciplined, you can use it in a way where it's always precise. For us, in describing how these fold operations are going to work, it's really the appropriate thing because it tells you just at a glance what this thing does. Right? So if I write this here, that tells you exactly what's going on here. We've got a list of elements x1 up to xn, and here they are all added up plus the 0 thing at the start. Because we could have replaced the 0 in the sum definition by anything, right? and then it would just be a different starting point. So you could put a 10 there, and then it'd be 10 plus the elements of the list. Right. This fold operation, it can seem a little mysterious when you see some of the examples, some of the ways it's used, but it really is conceptually no different than sum. All we're doing is taking the parts of this definition of sum that we had and replacing them by variables. So they're now things that you can feed in as parameters instead of having them fixed in the definition. So what we have here, this definition here is really the same thing as the regular sum that we defined, but where we've, think of it as abstracting out some of the parts, making some of the actual constants in there abstract entities. So replacing the 0 in sum by the variable z, and replacing the plus by some function f. And of course, where do those come from? Z and f, they're variables, they have to be declared somewhere. So the logical thing, really the only choice here is in the definition, you have to take them in as parameters. So the abstract sum operation, instead of having a fixed 0 and plus in it, now it takes those things as an argument. So it takes a z argument and an f argument, and one of the possibilities for those things is using what we had for sum. So maybe I should write that out explicitly, just to make sure, make clear what the correspondence is. If I take all right, so if I take this abstract sum here, and I give it as arguments, well, it takes a function first, so if I give it plus, plus is a infix operation, I have to put parens around it to make it a regular function. Abstract sum and 0, okay, then that is exactly what we started with. That is sum. And if you want to think of it as having a full argument list, I'll give it the argument here. We can write it that way too. Okay, so abstract sum plus 0, list of integers i's, is the same thing as adding some i's. And if you want to think it in terms of dots, notice I'm using this backquote notation here again. I'm doing that because it's just, it looks nicer because, for example, here you can see that we're taking two things and connecting them by f. If I had to write f out front of those two things, you kind of lose the pattern here. It would be much uglier and harder to understand. But if you look at it this way, it's, I think it's more clear what's going on. So what's happening in abstract sum here? Well, if you think of how we actually apply it, if you're doing abstract sum of some particular list, what does it do? Well, it takes the first thing of the list, right? So that's x here, and it connects it via f to the result of doing the same thing for the remainder. Right? So you can see here here's the first thing, and here's the f that we're using to get our result, and the other argument for f is the recursive part. And then you just keep going here. So basically, it's all of the list elements strung out, all connected by f. It's a little clearer, I think, if you write it without parentheses in the case where the function is associated. So if this is an associative function, it doesn't matter how it's parenthesized, and so we can actually write it without parentheses, and it'll be unambiguous. And if you do it that way, then it's a little more clear, I think, than what's going on here. So it's, x1, x1, f, x2, dot, dot, dot. And then finally you've got that z, that 0 thing. Oops, we needed an operation in there. Let's squeeze that in. Okay, so it's just all of the elements of the list strung out with z at the end, connected by this f. So f can be any operation at all. You can just think of it as plus here if you like. They're all integers, and we're just adding them all up, using the z at the right as a starting point. But it doesn't have to be an associative operation. We'll see some interesting examples where it's not. So we really do need to think of the parentheses there. The point is that what I've done here, I've called it abstract sum, but it is just this fold operation. That is the definition of what we're going to call fold R. So you can see these definitions look the same, right? So fold R, what did I get the? There's a, yeah, so there's an argument missing. Oh, sorry about that. Yeah, so this, I forgot the two arguments, so they have to tag along. F and Z. They don't change as you make recursive calls. They're just tagging along because they're you think of them as the parameters to the function. All right, so here, and it's consistent in my error here. Points for that. And here, there's supposed to be an F and a Z as well. Right? Right, so in the empty list case, well, that's what that Z element is for, exactly. It's where you start. And then for a case where you have a non-empty list, take the first element and then do your work on the remaining ones, add those all up, and then finally take that and use your, add that to X. I'm saying add here, but what I mean is, of course, use whatever F happens to be. So that's the whole thing. It's a very simple definition, but it's not as easy as you might think to actually use it in practice. There's lots of, if you're just doing it for something like sum, that's quite simple. You're coming up with a very simple value, just a number. You're summarizing the whole list as a number by adding everything up. But you can build more complex objects. You could take this list and do a fold operation and come up with another list. Why is it called fold R? Well, you can see it's because really the action starts on the right-hand side. So if I just have the x1 here, f, well, the second argument, I can't do anything with it until I've expanded it out. So I don't actually start applying f until I get down here. If you want to think of it operationally, that's what's happening, right? You have this list. You're applying some fold operations. You've got this f that you're trying to accumulate over the list. It looks at the list, sees it's not empty. So it wants to, let's just think of add, f being add now. It wants to add x, the first thing, to the result of adding up the remainder. Okay, but it can't do anything yet, so it has to make a recursive call on the remainder. And then again, so you make all these recursive calls until you get down to the end, where you have to say one thing left. And now you can add it to the 0 element. When you see the thing with the last thing in the list, yeah, there'll be another recursive call, then it will see Z because it's the empty list. And so when you back out, you get Z as the result from that recursive call. Now you're adding the last thing to Z. And then you can back out, you're adding x minus 1 to Z, to the result of adding xn and Z. Now you've got the last 3 added up. You can take the third from last and add that, and just keep backing up all the way out. And then finally you add the very first thing in the list to this big sum you've accumulated. So that's operationally how it's working. Starting at the right with that Z element, and then successfully adding up as you go to the front of the list. So that's why it's fold right. And there is obviously a fold F that goes along with it. It does exactly the opposite. But it really changes the kinds of functions you can define. Sometimes it's much more convenient to use fold L than fold R. So let's look at just a simple example here. It's, I don't know why I put this concrete example up at the top. This function concat is defined in the prelude. You probably maybe used it so far. It's just something which takes a big list of lists and strings them all together. It combines them all using append to make one big list, flattens it all out. Okay, and recursively it's defined, very straightforward. It's just a usual recursion pattern. I want to concatenate a list of empty lists. If there's nothing to concatenate, then I've got nothing. If there's a first element, right, so maybe I should have used a different variable here, but this is a list of lists, so X is some list. We recursively concatenate the remainder, and then we append X to the front of that. So is it clear what concat does? You can see I do have an example here. So just the elements from left to right, all in one big list. All right, so the point here is that you could define it this way. It's a reasonable definition. But if you get proficient with fold R, you can often roll up these kinds of definitions much more quickly. Yeah, you can write recursion. That, it's thinking at a different level too. Now I'm thinking about each individual element of the list and how I break things apart and reassemble. That breaking apart and reassembling is already done for you by fold R. So why not use that to eliminate some of the work that you're doing? So fold R here, this is all there is to it. It's just this, this little tiny one-liner here. Okay, so that's tiny. Okay. So it may not be so obvious why that works right up front, or maybe it is. I remember when I started functional programming, I found fold R to take, it was a very unfamiliar way of doing things. It took some thought to get used to it. But if we look at just the definition that we had here, if we think of the recursive definition of fold, then maybe there's a little work to do. But if we just think of this definition here, so this way of viewing it, remember fold R and abstract sum are the same thing. If we think of this definition, right, where we just have the elements strung out and we're connecting them all with a given operation, well then we can write it down just like this. But as I said, since it's an associative operation, we don't even need the parentheses. You can just think of it as this. Right? This is, since plus plus is associative. Right? And then it's very clear what it does. Just, I've strung out all the lists that are elements of the given list, L1 up to Ln, and I've connected them all with append. So just append them all together with the empty list at the end is irrelevant. This is usually the best way of thinking of, not in terms of the recursion. It's often the best way of thinking about what it does to the whole list in one shot. You get the list, and then I'm accumulating this value or coming up with this value for the whole thing by connecting all the elements of this operation. Okay? In this case, the operation is append. All right, so I'm not sure if I'm going to do this. I'm going to leave that as an exercise. I would do, just try this out. Use the definition of concat. So the first step would be to plug in the definition of concat, which is fold R. So this equals fold R of plus, and we'll do this. Right. Just do some equational reasoning with that using the definition of fold R. Fold R has this official recursive definition here. Just apply that bunch of steps to get the result of this. I think it'll be quite illuminating if you're having trouble understanding. If it's not completely clear how this is working, I think running through that will be a really good exercise. So you do that one. I want to look at a few examples of fold R. You'll have that so on an assignment some more. Just a few other examples here now. Okay. So let's take a quick look here, and then I'll show you some actual code. There's not a ton of code here. These things tend to be very short. Fold R, you can actually define a lot of the stuff we've done so far. Map and filter, you can define using fold R. I'm not sure, it's not going to clarify things for you because the definition of map and filter recursively is quite straightforward and tells you exactly what's going on. SNOC is backwards of cons. It's just, all it does is it takes an element and instead of sticking on the front of the list, it sticks on the back. That's like the Python append operation. And reversing a list. I'm not sure why I put those things on the slide here. They're in the code file, so let me just move to that. And laptop. Okay. If I made that a little smaller, people would be able to read it. No, I guess I can. You know what? I think I'm going to do it. Oops, sorry, no, that's small. I'm going to do one on top of the other. Very small. All right. All right, so I'm hiding these things, map, filter. Oh, I never did zip with. I encourage you to learn this. It's a handy function. It's not exotic. Just take a quick look here what it does. If you look at the type, it just has an info here, zip. It's just a very handy function. Do people know what zip is? Taking two lists, making pairs. Zip with, actually, why don't we just do, here's a simple example, which will tell you exactly what it does. All right, so I'm going to zip with plus. So you can see the argument I give it is, the function argument is any two argument function. It takes a list of things of the first argument type, a list of things of the second argument type, and gives you a list of things of the result type. So it's kind of obvious from the types what this should do. You've got these A's and these B's, and then a function which works on A's and B's, you need to get something of the result type of the function. You just go through the elements in order. Each time you get an A and a B, you apply it, give a function to it, gives you a C, that goes into your result list. Right, so let's just look at 1, 2, 3, 4, and 4. Okay, so it added the 1 and 3 and 2 and 4. Right, so just goes through them in order and applies the operation to see the result. Quite handy. And the normal zip function is just zipping with pairs Right, so that's handy. I don't know why I put it up here. Yeah, no idea. So I'm hiding map and filter here because I'm defining it myself. And this is not the file I wanted. I wanted to actually develop these, but oh well. No surprises here. So these, the map, doing map and filter using fold, it's, I would not say that this is a better way of looking at it. We're starting out with this just to give you an example of the kind of the generality of fold art. And it kind of subsumes these other things, but it is not the clearest way of talking about map. So we want to define map using fold R. We need a 0 element to start with. So what happens if the list is empty? What should be the value of map on the empty list? Well, it's empty, right? So that tells us what this that argument should be. And then we have our list argument, of course. The only work then is coming up with the actual function. So we've got, I want to think of this as being, this L is some list of things, x1, dot, 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 xn. We want the result to be f of x1, f of xn. And somehow that's supposed to be the result of doing some kind of accumulation. What we want to do is we want to have some operation, let's call it, let's call it operations. We need to come up with, just make this comment, just make it clear what we're saying. We have that input L, and we want to output that. And what we need to do is to come up with some operation such as the following holds. And let's just forget the parentheses for now. So what we want is that x1 op, x2 op, xn is equal to the result we want. Right? So there's the z at the end. And we've already said what the z is, it's the empty list. Okay? So we want that to be the same thing as f of x of x1, dot, dot, dot. I'll put the 2 in there as well. x2, and f of xn. All right, so if you think of it this way, then look at the last part. Say, you just think of the end of the 2 lists. So if we look at these parts, so they'll highlight them here. So it's just fold R. So that's the first operation that gets done. Although that doesn't really matter so much here. And then let's look at this. This is the end here. And you can think of that as being the same thing as, since we have this 0 element to deal with, saying this part of the list here, f of xn. Now that's the same thing as saying, f of xn corresponds to the empty list. Oh, it's helpfully giving me a new line there. Oh, stop that. Okay. All right, so if you think of it this way, so at the very end here you have, xn const onto the empty list. And then the second last, if you think of the second last element, that's f of x minus 1 const onto f of x n const onto the empty list. This kind of suggests what you need here, because what I want, this is supposed to be the result here of doing the operation with the corresponding elements. So what we really want here is that this fxn const onto the empty list should be the result of applying this operation we have to come up with to xn in the empty list. Right? So to take xn in the empty list and get this part here, what do I have to do? How do I turn this into that in a way that works for the remaining ones too? So just think, when we start moving back through the list, we don't know that it's the empty list, it could be anything. So let's just treat that as a black box. What do? You take, we've got two elements for the operation, we've got xn and the second one, and we're taking f, applying it to the first thing, and then just using the second thing there. Okay? So that tells us exactly what the operation should be. It takes the first thing, which is a list element, and it takes this result. I've used ACC here because I'm thinking of it as an accumulator. It's accumulating the results of doing some chunk of the list. It starts out as the empty list. So it takes that, it takes a second argument, and then just like in this part here, it takes f, applies it to the first argument, and just shoves the second argument in. That's the second part of the cons. And if you want to think of this in terms of how it works actually operationally, you think of it starting as the right, and then we back up through the list using this function over and over to accumulate results. So what does this function do? Suppose I've accumulated some result for some tail of the list. Then what does this function do? It takes the current element of the list, it takes the accumulated result and sticks x on the front. Or f of x on the front, sorry. So what I'm doing is I'm coming up through the list, start with the empty list, then I cons f of the last thing on, and I cons f of the second last thing on, and as I go through the elements, I keep consing f of those things onto the list, and in the end I end up with the map, having mapped f over the list. Okay. So I think I'm not going to go through the details on the filter here. I think it's worthwhile you understanding how this one works. This is a little different because you're not keeping all of the list elements, some of them are being eliminated. But go back to the definition, look at both ways of thinking of fold, the recursive definition or the one where you view the list as a whole. And probably the latter one will work best for you. And convince yourself that this really does the filtering operation. All right, the one last example I wanted to look at here was this way of doing the reverse. I'm wondering if I should bother with that. I think I'm not. I'm going to skip that too. So take a look at both of these. Basic idea with reverse is, again, you're going from the right and building up. As you see, you're accumulating this result, which is the reverse of what you've seen so far. You see a new element. How do you reverse everything in the list from that element on? Well, you take reverse of the remainder and you stick that element on the end of that. And that's all that's going on here. But it's worthwhile expanding it a few steps or trying it out and really understanding why this folding operation is the right thing for reverse. Okay. All right, so I think let's go back to the slides here. I just wanted to go do fold L and yeah, okay, so there I see a good stopping point within the next few minutes, and let's just do that. So let's go back to the slides here. All right, okay. Fold L is the left analog of this. I think I'm not going to go into detail on this because it really is analogous. There'll be some exercises in an assignment that where it's more appropriate to use one than the other, but kind of at a higher level, they're kind of interchangeable. It's just more a matter of what's a more convenient way for any particular problem. Fold L it does exactly what the other one does, but it starts at the left end. So you can see if you want to write down or do the expanded version, this is probably the easiest way of thinking about it. And again, if the operation is associated with getting rid of all of those parentheses, it's a little easier to read. This F is associative. Right? So we're just combining all of these things using the given operation, but we're starting at the left using the given starting point, Z. The definition looks a little different. The first case is the same. If the list is empty, then we're just returning the starting point. But in the case where the list is not empty, you'll see this actually looks a little bit different now because we're making a recursive call, but we're changing the zero argument. So that's a little different. The other one looks more like a generic kind of recursion where we just call on the remainder and then use that. But here, so just to point out here, just to be clear about this definition of fold R that we had, you can see that these, the F and the Z, they're just tagging along. They're just like parameters. Here though, with fold L, we're actually changing one of the parameters in the recursive call. So the way we do this, we need to add from the left end to the right. So that means if we see an element at the beginning, what do we have to do? Well, we want to add that first to all of the things in the remainder, starting with the second one and the third one. So the only way of doing that is to add up the things in the remainder with a new zero element. So you want to say, well, I want to add up those things, but I want to start with what I already have, or I want to start with this X, in this particular case here, right? The sum I'm looking for, again, we're just thinking of F as being sum to make the discussion a little easier. Thinking of summing these things up, but I want to start the sum, in this case here, with this Y. So Y has to be at the very beginning. And in this picture here, the thing that's at the very beginning is Z. So that means I have to change the Z to be this new beginning. So to start a sum of all the things in Y up to end YS, starting at Z, is the same thing as adding Z and Y, starting with that, and then adding all the things in YS. So that gives you this definition here, and this is actually an example of a tailed recursive definition that we'll talk about in a bit. But the thing to note here, and I've done this example here, I'm not going to go through it right now, but it's just applying the definition over and over. The thing to note here is that this fold L is on top. With the other fold, we had as we expanded it out, we had a bunch of things added, like 1 plus 2, and then a recursive call. So the recursive call is embedded in a bunch of operations. And what that means in terms of actually running the program is that you're adding 1, adding 2. You can't do any of those additions until the recursive calls are completed. So you have to expand out all of the recursive calls, and then you can start folding up your answer. But here, this thing's always at the top, which means it doesn't have to wait for anything. So this one call to fold out at the beginning, it makes a recursive call but there's nothing to do to the result of that call. We don't have to add anything to it. The result of the second recursive call is the result of the first one, first function call. And same thing with the third one. So that in a nutshell is the notion of tail recursion. We don't need to build a stack, right? As soon as you make the recursive call, that's going to be our answer, so we can just forget about that first call, and now we're just working with that second one. So there's no stack to build. So that sounds like it should be a lot better, but we'll see an example where it's not. So please do go through this example and convince yourself it's right. And also do the same thing that we did for cat with this fold-L version. You can find it, this is the same definition as we had before, except we're using fold-L instead of fold-R, but it executes in quite a different way. That's worth seeing. And now just last thing, a summary of the things that we've seen so far. This is what I'm going to call our higher order toolkit. These are things that are all good to know. I said $sign, you don't have to use it if you don't want it, it's just a syntactic convenience. But the other things you should know. These are all important tools in writing higher order programs. And if you just know these, you'll be able to do a lot. Okay? Next time we'll talk briefly about tail recursion.